Hi, we're going to take a look at a few more examples of all of our different power theorems. So let's start with a chord power theorem. Notice that in my picture, we've got one chord that has the sides of 12 and 9 minus 4x. That creates one chord. And then our second chord is made up of the two segments of 14 and 3 minus 5x. So once again, as the chord power theorem states, what we want to do is multiply each of the pieces together that form one of the chords, and we set those products equal to each other. So since 12 and the 9 minus 4x form one chord, those get multiplied together. So notice 12 has to get multiplied by that entire binomial, so that's why I put the binomial in parentheses. And then we'll do the same thing with the other product. 14 has to get multiplied by the 3 minus 5x, and once again, that has to be in parentheses because that whole binomial is getting multiplied by 14. So I want to start distributing. When I distribute, we'll have 108 minus 48x. We'll distribute on the other side as well. So that gives us 42 minus 70x. Now our goal is to start solving for x. So I want to get all the x values to one side. So I'm going to go ahead and add 48 over to the right. That still leaves us with 108 on the left. We'll still have 42, but now we'll have a negative 22x. We will then move that 42 over to the other side by subtracting. That gives us 66, and that equals negative 22x. So then last step to divide by negative 22, that will get me my value for x. X equals negative 3. I know that I forgot to write the directions, but all I wanted us to do was to solve for x. So we are done. So once again, chord power theorem, you're setting each of the segments that form one chord. By multiplying them together, you set it equal then to the product of the two segments that form the second chord. If we look then at a secant power theorem here. So we have two secants because we have two segments that intersect the circle at two different spots. Notice that they touch a point that is outside the circle together. So remember, our thought process was, let's think about that phrase, we, whole times exterior equals whole times exterior. We'll notice that the whole entire secant here is us adding those two little pieces together. So I want to add x plus 5 plus 8. So when you're looking at your like terms, notice that the x will stay as it is. 5 plus 8 is 13. There's my whole piece. So x plus 13 is the whole piece. That has to get multiplied then by the external part. Notice that my external part is 8. I'm going to go ahead and put that external part first, but there's my product of that secant from the top. We're going to set that equal then. Now I want the whole entire secant over here. So once again, that's a matter of us combining like terms. So I'm going to add the x plus 1 plus the 9. Once again, x will stay as it is. 1 plus 9 is 10. That's my whole piece. So x plus 10 represents the whole secant there. The external part is 9. Once again, I'm going to put the 9 out in front. All right, so once again, now that we have everything set up, all I want us to do is solve for x. So that once again involves us doing some distributing. So when I distribute the 8 times x is 8x, 8 times 13 is 104. On the other side, distributing, 9 times x is 9x, 9 times 10 is 90. To start getting x's together, I'm going to subtract 8x. That still leaves me with 104 on the left. Now I only have one x, still plus 90 on the right. We'll subtract 90 from both sides. And that's why we'll get a value of x to be 14. And once again, that's all I wanted. So 14 is my answer. Our third and final is another example of a secant sequence. Okay, notice that I need to combine these together. So I'm adding x minus 4 plus x minus 2 to get the whole piece. Well, x plus x gives us 2x. Negative 4 minus 2 gives us negative 6. So once again, if I'm thinking whole times external equals whole times external, then I want to take the whole piece, which is this 2x minus 6, and multiply it by the external part, which notice is x minus 2. On the other side, the whole entire sequence would be us adding those pieces together. So that would be 8. Our external would be 3. So on the left, notice that we have two binomials. When I distribute that out, we'll have 2x times x, so 2x squared. 2x then also needs to get multiplied by negative 2, so that gives us a negative 4x. Distributing the negative 6 to everything in the second parenthesis gives us a negative 6x and a positive 12. On the right-hand side, 8 times 3 gives us 24. We have several like terms, so 2x squared is still the same. Those x's, though, combine into a negative 10x. We still have plus 12 equals 24. Because there's x squared, x, and a number, I want to get all those terms to one side. So I'm going to move the 24 over to the left by subtracting. That gives us 2x squared minus 10x, now minus 12, that equals 0. This is a factoring problem. Can't just solve for x if there's both an x squared and an x. First thing we do when we factor is look for a GCF. Notice that every single one of those numbers are even, so they all have a 2 in common. So by factoring out a 2, that leaves us then with an x squared minus 5x minus 6. Because I then can now continue to factor, I want to know what multiplies to the last number but adds to the number in the middle. Got to keep that GCF there. Because there is no number in front of the x squared, that means I start off each of my parentheses with an x. Numbers that multiply to negative 6 but add to negative 5 are going to be negative 6 and positive 1. To solve for x, any factor that has an x needs to be set equal to 0. Because that GCF does not have a variable, I can now ignore it. But the x minus 6, that factor needs to be set equal to 0. And then the second factor of x plus 1 needs to also be set equal to 0. So notice that involves us adding 6 to get us one answer to be positive 6. And then we'll have to subtract 1 to get another answer of negative 1. Now remember, x is representing, in this case, part of a segment. So because there are two potential answers, it is important to make sure, are these truly going to work in my diagram? So if I go back to the original problem, notice that if I tried to substitute in 6 and we're determining that this is helping us get the length of a segment, I need to have a positive length. So plugging 6 back into the x minus 4, well, 6 minus 4 is positive 2, so that part is okay. Plugging 6 into that second x on the external part, 6 minus 2 is positive 4, positive number, that's okay. So 6 checks out, that will be a solution. Notice that when we try to plug negative 1 in for those x values, negative 1 minus 4, already off the bat, that gives me a negative length. I can't have something representing a negative length, so that means that this is truly not an answer. So out of those two, only one of them works.